Good morning. I'm Kathryn O'Brien from IBM Research. As Michael said, I've been working at IBM Research for a long time. My background is in compilers, and I hit this. Okay, so I wanted to talk about OpenMP in the era of Exascale. As Michael said, OpenMP has its 20th anniversary this year. IBM has been involved in OpenMP for as long as it's been around. And we've had some very good success stories, not only in compiler implementations of OpenMP, but also in actually helping to drive the OpenMP standard. I chose to talk about OpenMP in the Exascale era because I've been heavily involved in the CORAL program, and the CORAL systems, I think we would agree, are the first pre-Exascale systems. But this chart is really just a high-level conceptual chart of where we are on the roadmap to Exascale. And one of the things I'd like to point out is that it's as we drive towards Exascale, the applications are changing dramatically. So if we think about in the early 2010s, in the Blue Gene era, the real focus was on the performance of HPC applications, LinPack and the top 500, that kind of stuff. Looking forward to the true Exascale systems in the early 2020s, we're beginning to talk about machine learning, cognitive, and what the architectures are that are going to, support those kind of applications. Back in the Blue Gene days, well, I guess I should say, as the applications require more and more compute and have to handle larger and larger data sets, the architectures are becoming more complex. We're getting heterogeneity in the compute, heterogeneity in the memory, and this, of course, puts a burden on the programmer how to deal with all this complexity. But if we think back to the Blue Gene days, the focus there was not on heterogeneity or different types of memories, but how to deal with large number of threads, and trying to get application developers even to think about threading their applications was a huge issue. So moving forward, the programming models for these architectures, programming models have always been the bugbear of system architects, and that continues to be the issue as we move forward to Exascale. Okay, so the architectural complexity, it doesn't just involve the programming model, it impacts all aspects of the system software stack and the execution environment. The operating system and the runtime, I mean the operating system has to, as we move forward to heterogeneous systems, we don't even have operating systems on the accelerators. We have to have extensions in the kernel. There's very complex control systems, resource managers, schedulers. Debugging becomes a nightmare. And all this, as I said, this is all going to increase significantly by 2022. Heterogeneous compute and memory, different memory attributes, non-volatile memory, how that fits in the system, how the user works with non-volatile memory, managing the huge reams of data, and of course resiliency. So imagining that we can get all this complexity supported in the system software is one thing, but assuming we do that, then the programming model is the interface between all that complexity and the application developer. So not surprisingly, focus on the programming model has been a major part of the move forward to Exascale. So what are the constraints of a programming model? A programming model has to be all things to all men and women and application developers. It has to address a broad range of expertise. It has to address the very experienced programmer. It also has to address the low level of programming expertise. Everybody wants to be able to develop their applications quickly, deploy them rapidly, but performance is paramount. We need to provide high-level abstractions with breakout mechanisms for critical performance paths. More importantly, we need to provide a migration path for legacy codes and cross-platform performance portability, and then we have to support a large range of implementation paths. People want to use libraries, they want to use languages, new languages, compiler extensions, pragmas, directives, and then, as I alluded to earlier, there's huge barriers to adoption. Just getting people to thread their codes, 5 to 10 years ago was a huge issue, and actually continues, even for some people to get them to move to threading is still an issue. So the application programmer's dilemma. On the right-hand side, we have the pipe dream of all application developers, which is automatic optimization. So I spent probably 20 years of my career working on optimizing compilers, developing techniques for auto-parallelization, locality optimizations. In the days of Cell, we did automatic DMA optimization. We had done some work on speculative parallelization for the PERCS project using helper threads. And over time we came to realize no matter how good your dependence analysis is, no matter how good your compiler is, there's just so much information that you don't know at runtime that getting good automatic optimization is really difficult. When we started to work on this Cell project, I think that's when we began to realize if you really want to get the best code, you need to start thinking about using hints in the compiler, or a combination of hints in your code, and maybe a combination of hints and runtime techniques. So while on the right-hand side, optimization is obviously the best approach for the user, it doesn't get the best performance, and it is frequently spotty. Very few compilers are really successful at across-the-board automatic parallelization. Then if we look on the left-hand side, if you really want to get the highest performance, you need the most intervention by the program. You need to use manual techniques. You need to do manually unroll your loops, and you need to pore over your code and determine what the best iteratively look at your source code, look at the code generated, try out different techniques. And the one thing I'll say is when you get the best manual techniques, quite often your compiler will screw that up. So you put all this work in and you still don't end up with the best performance. So I guess over time I would say we've kind of acknowledged that automatic approaches are not going to cut it. People don't really want to put the effort in to do the painful manual techniques that may get undone. So we're kind of settling in this middle area here where we use a combination of higher level pragmas and directives, which has the advantage of preserving, hopefully, the readability of the code, so you get better performance with less outlay and hopefully good performance. So that's kind of the dilemma that we see for the programmer. Okay, so going back to my roadmap, So looking back to the Blue Gene era, that's also the time when we started to think about the path to exascale. 2008, 2009, there were many, many workshops. There was the IESP, the International Exascale Software Group, that met on a regular basis at locations all over the world. And the purpose of this was to define the architecture, software, etc. for exascale, and one of the big focuses back then was on programming models. So in those days, exascale was 300 petaflops in 2015 and an exaflop in 2018. So back in 2008, 2009, there was a report on, there were reports on all the different aspects, but the report on programming models concluded a number of things. Essentially, they said that new programming models would not be feasible in the 2015-2018 timeframe. If you think about it, if you want to get a new language with a standards group and an accepted standard, I mean, that's like a minimum 6 or 7 year effort, assuming you've even agreed on what the language would be. So the notion that you would be able to have a new programming model in 2015, 2018, back in 2009 was deemed to be not feasible. What they recommended was to invest in a range of existing programming models, monitor the current programming models outside the exascale community. In those days, that was things like CUDA, OpenCL. Evolve the existing hybrid programming models, MPI and OpenMP. Look at developing new hybrid models like MPI and PGAS. Not sure why anybody would want to do that, but it was something they were thinking of. The holistic models like CORAL, Fortran, UPC, HPCS were still considered reasonable approaches, especially if you were looking for a system-wide programming model. But the conclusion was that totally revolutionary approaches were not a good idea. It was unlikely that revolution would happen. But of course, since there is a research component to this, we don't want to throw out the notion that it's possible, some new language will kind of magically appear that will make everything easy, but in general the consensus in 2009, 2010 was monitoring the existing languages. The one thing that they did make a note of was that the abstract machine model was changing, and there needed to be a greater focus on intranode. This is when we were beginning, this is around the time, I guess, with kind of just maybe finished with cell back then, I think. So cell, the cell architecture, I guess, was the first hybrid architecture. It had the power processor and the SPUs, and programmability was not the strong point of that. So we were beginning to understand that there was going to be more focus, intranode, and that the HPC programming models were not really, they tended to follow rather than lead in the area of acceleration. Okay, so going back to my conceptual roadmap, so fast forwarding to where we are today, so we're very soon going to see delivery of the world's first fully data-centric systems, the Sierra and Summit systems that will be delivered to Oak Ridge and Livermore. So the roadmap to exascale, to these pre-exascale systems, has been an exercise in co-design through collaboration. So these multiple collaborations, actually. So the CORAL systems are a combination of IBM, Mellanox, and NVIDIA technology. In 2014, we were awarded a large contract to build these supercomputers. for Oak Ridge and Livermore. Oak Ridge had experience with heterogeneous architectures in the Titan system, but for Lawrence Livermore, the move to a heterogeneous architecture was a big jump. It was a big shift to think about moving your applications to something, a very different kind of architecture. So one of the major concerns as we started off on this journey was that on day one we would have applications ported and ready to run on these systems. Also that the codes that would be ported and running on these systems in day one would still be running on in 10 years' time and would be available for, you know, the evolution of architectures. So a large part of the, not a large part, a significant part of the program was we had an NRE portion that was developing software for these architectures, and a significant part of that NRE was the establishment of centers of excellence. So we have 3 centers of excellence. So the notion is that we have IBM application team members on site at both Oak Ridge and Livermore, working very closely with the applications team. So we started out with a center of excellence at Livermore, and then we very quickly added an extension to set up a center of excellence at Oak Ridge, and then subsequently we added another center of excellence at Livermore to deal with their institutional codes rather than their mission codes. And the way those, the idea behind the centers of excellence is that at Oak Ridge they have their CAR codes, which are people apply with their science applications and get selected, and then I guess Oscar's here, he knows about the CAR applications, and so the CAR teams work with the IBM team to port these applications. The problem with this plan, of course, is that we didn't have compilers, we didn't have systems, so getting up and running to get these application centers, these centers of excellence, was quite challenging. But fortunately at IBM we had been working on some compilers for a research architecture and active memory cube architecture, and we had started to do some work on developing an LLVM compiler for heterogeneous architectures, and we were able to shift gears very quickly when the program started and start to develop an OpenMP LLVM compiler for the CORAL architecture. And actually within I guess the first 6 months of the program starting, we had a compiler that the application developers were able to start playing with. It wasn't, it was a very raw compiler. They were rapidly working on function, but at least we had something for people to work with to start porting these applications. And this turns out to have been a very key part of the program. So just confirming what I said, if you look on the exascale.org website, there's lots of stuff about the delivery of the Summit system to Oak Ridge. They talk about the CAR users. They're actually installing the systems right now. I think we're currently a week ahead of schedule. I think the Livermore systems are a little bit further behind, but still in progress. And as they say, I mean, it'll be 2019 before, you know, all the users are on board with these. But by the middle of next year, we expect people to be fully exercising these systems. And yes, we will have compilers, OpenMP compilers for users to use on these systems. Okay, so in 2016 we released the Minsky Systems, which was an early an architecture based on the Power 8 and the Pascal GPUs. The labs and other people got early access to these systems, and so that they could, be able to start porting their codes and have an idea of what the issues were. So I'm just going to take a little look at some of the work that we did to enable high-level programming for these OpenPOWER Minsky architectures. And most of what I say for OpenPOWER also applies to the CORAL architecture. Okay, so from a compiler viewpoint, the OpenPOWER architecture looks like, on the left-hand side, we have the fat cores with 8 SMT threads per core, 160 threads per processor. There's complex branch prediction and an out-of-order pipeline. On the right-hand side, we have the highly parallel CUDA cores, highly parallel GPUs with order 10 to 15 threads per device. Thread divergence is serialized, and there's limited synchronization within the CUDA blocks only. In terms of the memory, on the power side, we have the very large caches. We have low memory latency, and we can optimize for cache locality. Whereas on the GPU side, we have caches that are relatively small on chip, small compared to the number of threads. The L2 is off chip, something equivalent to the L4 in the P8. And here we want to optimize to hide memory latency by using lots of in-flight threads. So if you think about it, the OpenPOWER architecture is focusing on flexible acceleration. So we believe that it delivers the best performance beyond the HPC field. There's a balanced combination of the power processors and the GPU accelerators. But going back to my theme, how do we effectively and efficiently program this OpenPOWER architecture? So what are the programming options for this architecture? So we considered what our options were, how to program this mix of large fat cores and small thin processors. The options really, if you look on the GPU side, you have CUDA. You can use CUDA with C, C++, or Fortran. In terms of high-level constructs, I would say there aren't really any high-level constructs with CUDA. So what companies or organizations are actively involved? Well, we have NVIDIA, PGI, and IBM, to the extent that IBM, of course, you can use CUDA with our XLC compilers. We did also develop a CUDA Fortran compiler. And CUDA is available only on the GPUs. You can move up a notch. You can move to a higher level programming model for your GPUs by moving to OpenACC. You've got parallel, loop-like, and SIMD constructs. It's supported by Cray, PGI, and I think there is a GCC implementation also. And it's targeted for GPU-like accelerators. Well, then we looked at, if you do that, you still need to worry about how you're going to exploit the parallelism on the host. So if we look at OpenMP, it has all the high-level constructs, the parallel, the loop-like, the SIMD, the tasking. It's supported by a broad range of companies, IBM, AMD, Intel, Cray, Pascal, TI, etc. And it features mostly architecture independent flexible parallelism. So these were the options that we looked at for programming OpenPOWER. Then what are the what's on the wish list for the programmers who want to program this? Well, they want high-level parallel abstractions that are architecture independent. They want the ability to cover a high range of application patterns, dense, sparse, graphs. They want performance portability. They want a single version of a kernel to be able to run on both the host and the GPU. They want to get the best performance possible across both. They want easy incremental development. They don't want to rewrite entire applications in a new language, but they do want to be able to interoperate with assembly kernels and libraries. And they want continuity. And for continuity, you really do need industry standard languages and directives. And you want something that's supported everywhere and that it'll survive the fashions or trends in architectures. So we looked at the range of options. And we decided for easy porting, continuity, performance portability, high-level abstractions, that we were going to work with OpenMP as the programming model of choice for the OpenPOWER architecture. So the OpenMP 4.5 design goals: write once, run everywhere with the best performance. So, as I said, if you want to program a GPU, you have a range of options. CUDA OpenCL. If you want to program a CPU SIMD unit, you can use Intrinsics, OpenCL. You can possibly rely on auto-vectorization. If you want to program a CPU, you've got C++, 11, 14, whatever, thread building blocks, Silk, continuations, whatever. So with OpenMP 4.5 and up, you can use the same standard to program across this range of architectures, host and accelerators. So that was the choice we made. And so the OpenPOWER CORAL programming model roadmap that we laid out was, in the short term, we would propose OpenMP 4.5 and OpenACC, compilers available for both, provide interoperability with CUDA, of course, but in the longer term we're saying that we would drive towards OpenMP 5 as the dominant approach. We really would like to see a convergence in the standards. And there's a lot of people are actually thinking about what would a directives optional threading model look like that could support execution across a range of homogeneous and heterogeneous core types. That's, I think, not something we're going to see in the Exascale era, but it's definitely something that people are thinking about. So while the roadmap that we laid out says, we believe that OpenMP will be the dominant programming model on the IBM heterogeneous architectures, we do support a range of programming models. So you will be able to use CUDA with C, C++, and Fortran, with the host compilers being GCC and Excel. We do support OpenACC. In fact, as part of our CORAL program, we work very closely with PGI to develop their OpenACC compiler. We share a power backend in the LLVM infrastructure with PGI. So those compilers are available. And then for OpenMP, we support two compilers. We have the IBM proprietary Excel compiler, which supports OpenMP 4.5 for offloading. I think that compiler will GA at the end of this year. And we also, as part of the CORAL NRE, we developed, we had a project that has been developing OpenMP in the LLVM infrastructure. So that's the range of options for programming the OpenMP architectures. So I was just going to take a few minutes and kind of look a little more closely at the OpenMP programming model and why it's so suitable for this kind of architecture. So OpenMP, of course, is a fork and join model, right? The sequential code is executed by the master and the parallel code is executed by the master and the workers. The parallel region is terminated by a synchronization barrier, and the memory touched in the parallel region is released or flushed at the barrier. So that's kind of the high-level execution model. It provides flexible parallelism. You can distribute your code across threads if that's what your application or architecture prefers. We have done significant performance optimization for successive small parallel loops. On the other hand, if your application is more suited to SIMD deployment, you can use the parallel loops can be spread across your SIMD architecture. So there's flexibility in the way your parallelism is deployed on your architecture in conjunction with your application requirements. Another important thing is thread affinity, the ability to specify how your threads bind to cores or sockets or whatever to get the best memory usage in your architecture. So, for example, if you have small compute with lots of data, you might want to spread your threads across the sockets. If you have compute intense and you want to optimize for locality, you can keep your threads close on the threads within your core. Okay, so looking at taking the OpenMP standard, which is essentially a shared memory programming model, and now how do we use that for programming hosts plus accelerators. So the key construct in OpenMP is the target. So any code within a target region will be offloaded to your device, and the default map to from will copy your variables over to the device for the computation. Then you need to copy the data back out on completion. So on the device, we can see the same kind of flexible parallelism as on the host. For parallel loops on the GPU, each team, so we have this target teams. Each team corresponds to a CUDA block. The OpenMP threads are CUDA threads, and then the distribute schedules blocks of iterations to the teams. So SIMD inside Parallel is very widely used on the host to leverage the vector units for the threads. The GPU doesn't have vector units, but if you use the Pragma OMP SIMD, you can map your SIMD lanes onto CUDA threads. So we have the same kind of flexibility as you see on the host. Then the target constructs, they're implicit. If you think about it, they're implicit tasks, right? And a host can actually initiate several target tasks asynchronously. Those target tasks on the device may have dependencies, and those dependencies between the target tasks are resolved completely on the GPU without host intervention. So you can exploit the concurrency both within the host and the device simultaneously. The host threads, the host threads can take advantage of multiple GPUs in a node, so you can have asynchronous execution on multiple GPUs, and at the same time you can overlap the device computation and communication with the execution on the host. And again, the dependencies within the device are satisfied on the device. Sorry. PowerPoint has encountered a problem and needs to close. That was a reason not to use my laptop. It's out of it. Yes, my PowerPoint crashed and I'm not sure what's happening. I have it on, if I can't get it back, I have it on. I'm going to just reboot. Okay. Sorry. What is happening? No, but it's not.
Oh, isn't it?
It's crazy. I have my talk on a memory stick. If somebody has a laptop that I could.
I can pick my laptop.
Oh, maybe it's coming back. I think it's come back. Hold on.
Okay. It's coming.
I got it.
Yeah. With Kathryn. Yeah. Let's go. Back up and running? We're back up and running?
Yes, I don't know what happened.
It's probably running OpenMP.
It's like the phones sometimes in conference calls. They say they haven't had any input for a long time, so I guess it decided. Too much hot air. Okay, so I think I covered the main constructs for offloading execution to the device, but really the major complexity and performance concern in programming these heterogeneous systems is the data movement, right? So it's very important to minimize data movement, right? So you really need to understand the data scope, the data types that can be mapped, and the memory model. So we say here it's distributed memory in the current implementation. So I guess what we're saying is in our compiler implementation, we assume two distinct memories, the host memory and the GPU memory. As you're probably aware, the the Minsky Systems have software support for unified memory, which means under the covers, data is moved between the host and device. In the Witherspoon Volta time frame, there will be hardware support for that, and the performance that what they provide in the earlier systems is more functional than performing, but in the CORAL time frame that should be highly performing. So in theory you will not have to worry about explicitly moving your data. In the current implementation, we're saying that the memory model is distributed, and in fact that's what the OpenMP standard supports. So overcoming data movement is the big challenge. So for example, in the default, the data scope is limited by the target construct. So in an example like this, you would have to explicitly copy C between the two pieces of code inside the target region. So that seems like a little bit unnecessary. There are ways where you can keep C resident on the device, so that eliminates the copies. When you do that, then the map clauses are ignored. So if you want to explicitly reference your variable on the host, you have to use either the update or the always qualifier. I think that's the same. I thought I took that out. Okay, so then unstructured data movement, data that doesn't have a lexical scope. So the scope of duration is on the device is dictated by the runtime. You get that effect by using the enter and exit clauses in OpenMP. Then you can have some data always resident on the accelerator. And again, if you want to move that back, but you do this by using the declare target and declaring your data within that. If you want to move it back and forth, again, you have to use the target update. So the summary of the data scope, I guess the point I would like to make here is that managing the data is the most provides the most complexity in using OpenMP 4.5 on the devices. It's the thing that our users complain the most about, and there are issues still that are not resolved. Some of these issues, like the deep copy, how we deal with that. So something to be aware of, and something that we need to keep working on. Going back to this notion of the accelerator memory model, so if you assume unified memory, like on the left-hand side, the value of C, may change during execution of the target region. If you assume the distributed model, you clearly have to copy your data in and out. So there's issues to do with assuming the unified memory and using OpenMP. If you write your program without using the map clauses and rely on unified memory to do the copies for you, it's actually not a valid OpenMP program. And that's something that's a bit of a concern for some of our users. People want to be able to rapidly prototype their code relying on unified memory, then heavily profile looking for the hotspots once they understand the memory patterns within the program, then they want to use more specifically targeted data directives, so that it's a usage model that people are beginning to play with. From a compiler perspective, the compiler can selectively decide when to copy the data, but the thing is, to have a valid program, the user must still copy the, use the specified clauses to manage the data. Okay, so real-world scientific applications, things like multi-physics applications, they have different kinds of codes that want to be executed on the same architecture. So for example, if you have a graph-like workload that's highly irregular, that benefits from large caches, etc., you might want to run that piece of code on your host processor, but your data parallel pieces of your workload you might want to run on the CPU. So we think that this architecture in combination with using OpenMP gives you a very good flexible parallelism approach. How does OpenMP differ from your typical GPU programming model? Well, the traditional models, they say execute this one exclusively parallel loop, the way you do with your CUDA kernels. If you think about OpenMP, we like to say that it's just another normal OpenMP program on the device. What do we mean? You can leverage all the OpenMP constructs, parallel regions, parallel loops, tasks. There's fine-grain and coarse-grain synchronization, and you can have sequential and parallel code. OpenMP does support the traditional model too if you use the target team's distributed parallel for SIMD. And then here is just a list of the features in OpenMP, the new features in OpenMP 4.5. And I think if you look at this, you'll see that there's a huge amount of work, of additional features that have been added even between 4.0 and 4.5. And that's something that we need to be very careful about, because the more new stuff you're adding, it's this chicken and egg thing again, right? So these architectures are evolving, the standard is evolving to keep pace with the architecture, and everybody wants everything yesterday. So there's a lot of changes going in, there's a lot of need to keep backward compatibility, so just a lot of stuff going on, but I think the progress is really very good. Okay, just a little bit so as we work our way through, in the centers of excellence, of course everyone frantically wants to show the performance versus just executing on the host, or performance versus using CUDA. So we have a couple, we've actually published a fair amount of stuff with our LLVM compiler. So one example is this Kripke, which is an application that's part of our centers of excellence. So we started porting to OpenMP and CUDA at the same time. In the OpenMP version, we used the collapse clause, and it's hard to reproduce that effect in CUDA. So we actually were surprised to see that the OpenMP performance, the dark color, was significantly better. This is just in the first blush, was significantly better than the CUDA code. Subsequently, the CUDA code has been debugged to catch up. This is just the kernel that we used the collapse in. Another example was Lulesh, where we have for 5 5 of the kernels we get better or comparable performance to CUDA. There's a couple at the bottom that we're still working on where we have worse performance than CUDA, but if we can, you know, do as well or better, that's pretty good. Then this is a, I don't know if you can see it. So this is an example of improvements in the compiler. So our original code generation scheme was really very much targeted to the SPMD model of the GPUs and resulted in very complex control flow within the generated code, and also we weren't able to do nested parallelism. So we've recently reworked that part of the compiler and find that we get significant speed up. So the pink bars are showing the performance speed up versus the original implementation in the compiler, and the green and the purple are the speed up versus the existing GCC, OpenMP and ACC compilers. And these are a selection of kernels from SpecXL and others. So it's just really to point out that not only are we focusing on performance comparison with CUDA and GPU performance versus host performance, but we're constantly reworking the compiler the LLVM compiler implementation to you know, to improve the performance and get rid of overheads. So just some summary thoughts on all of that. As I said, OpenMP 4.5 is a relatively new standard, evolving to OpenMP 5. As I said, chicken and egg, the implementation of the compilers, the firming of the standard, and the porting of the applications are all happening concurrently. So the lessons learned so far from porting codes, and specifically from managing multiple memories, may lead to new features in the standard and also in the implementation. The IBM LLVM implementation is fully 4.5 compliant. We also do some prototyping of standards features. The experience so far in porting applications is positive. Yeah, I think I've covered most of that. So I have 5 minutes?
Sure.
Okay, so looking forward to Exascale. So here's a real chart of where we're going to with Exascale. Again, this is from the Exascale Computing Project website. If you look at where we are today, 2017, they're suggesting a huge leap in performance. So between 2017 and 2021, we're going to have a 5x improvement in performance. So the mind boggles at the architectural innovation that's going to get us there. So the issue of programming model is not going to go away. But if I look back now at what are they saying about applications and programming models, so you'll notice that this notion of data science, machine learning problems, in addition to the traditional applications, is very front and center. From a programming model perspective, exploiting on-node memory and compute hierarchies, achieving portable performance without if-defing code is a big issue. When they talk explicitly about programming models, so they say OpenMP represents a community standard, the ultimate objective of working effectively, blah, blah. The point of this is OpenMP is firmly fixed as a programming model of choice for Exascale. So in terms of strengths and challenges, what does that mean? So I would argue that the advances in the last 3 years it's very well positioned for this dominant role at Exascale. We've shown a significant amount of progress in evolving the standard to address the architectural complexity. We have reference implementations and research prototyping. And then there's the SOLVE project, which Barbara is the PI on. The SOLVE project is essentially being funded to do very much the same kind of thing that we did in the LLVM compiler as part of CORAL. Work very closely with the application developers, the standards committee, to make sure that OpenMP evolves to address the needs of the community. In terms of challenges, I would say the main thing is to continue supporting a broad range of heterogeneity. Right now we have NVIDIA GPUs. We need to be sure that the implementation is general, not just specific to NVIDIA. Performance portability, that's in progress. There's a lot of activity to ensure performance portability. Increased complexity, I think, is probably one of the major challenges facing the standard right now. If I talk to our users, that's one of the main problems. Backward compatibility, getting things right the first time. As I said, everything's happening very quickly, so that's something we need to keep an eye on. I would say broadening adoption beyond the current user community would be important. The more users, the more feedback. And then expanding into additional application domains like machine learning and AI, etc. In terms of performance portability, there's a lot of work going on. The Centers of Excellence, they have performance portability workshops. We've had several hackathons that produce very good feedback for the compilers and for the standards group. I think interoperation with DSLs, so at the last performance portability workshop, it got a little kind of hairy because every person new to this game wants to invent their own abstraction, their own DSL, but a couple are coming to the forefront, Raja and Cocos, and I think interoperability between OpenMP and Raja will be very important going forward. And I think one of the things that really would be good to see in the standard is some consideration of a descriptive capability versus the prescriptive. To some extent, an opportunity for the compilers to have a freer hand within the constraints of the programming model. This is just a chart showing work we've been doing on OpenMP and Raja and demonstrating that when using a comparison between using vanilla OpenMP and OpenMP within Raja, and except for the two outliers, the first two, we're showing fairly good performance with Raja. So, concluding thoughts. The programming model landscape is huge. It can be vendor-driven and proprietary. It can be standards-driven, providing a unified approach. And then there's, as I said, the research-oriented, that's where you get the plethora of abstractions. Very few new models have really caught on in the past 10 years. Many have disappeared, thankfully. The established hybrid models continue to have the most traction. OpenMP has made significant progress in the last 20 years, and I think we need to build on that and take it forward to Exascale. That's all I have.
Thank you.